So far in the project, I have been using the smaller dataset, the 100K rating dataset. And so the next step is to go to the full dataset, the 27 million rating dataset. But before I do that, I'll go over the techniques that I use to handle the big data problems. So the first technique is Pickle. So this is basically saving intermediate variables to disk. So here's the project documentation under full dataset, input and output files. So for example, the first time I run the Python script, it's going to read the CSV files. It doesn't have any variables the first time I run the Python scripts. And the very first time I have to read the CSV files, the original dataset from Movie Lens. And then when I figure out the variables, I'll save them to disk. For example, the genre IDs variable, that's a dictionary that maps from a string to an ID. So the string is like action or sci-fi or romance or thriller. And then the ID is some ID that I assigned internally to my software. So the first time I have to read the variables from the CSV files, but then I save it to the hard drive so that basically I'm processing this ID only once. The next time I need the ID, I just read it off the hard drive. And this is done using the Python Pickle module. Oh, so the directory structure is like this. The data/txt directory contains the original CSV files that are downloaded from the Movie Lens database. And then this is like the input. In stands for input. So these are variables that are extracted from CSV files. And then there's ALS. Those are variables for the ALS models. And out are like the variables that are needed by the final application. So for example, the similar movies database. And there's a flowchart in the documentation under data processing. So yeah, the input is in the txt directory and then it just flows out. And the final outputs are in the out directory and also in the ALS directory. Okay, so the next technique is multiprocessing. This is to run multiple Python interpreters in parallel. So in Python, there's multi-threading, but Python multi-threading is limited to one single core. So Python multi-threading cannot be used to increase performance in this situation. The Python way of increasing performance is to run multiple interpreters. And they call it multiprocessing because the name of the module is multiprocessing. So this approach has some limitations. So it doesn't work well in the interactive mode. So a lot of Python computing happens in the interactive interpreter mode. And that mode is tied to a single Python interpreter. And this technique, this multiprocessing package, this technique starts up multiple interpreters. So it's bad for interactive mode. And sharing data is another limitation. So this is the multiprocessing module documentation from the Python library. And sharing is limited to just values and arrays. So like very basic level data types, value and arrays like a binary array, like an array of bytes. You can also share C types, like over here, C types. Now, but this is not what most people do, right? People write Python programs, they use lists and dictionaries, lots of lists and lots of dictionaries. So out of the box, this multiprocessing module currently doesn't allow for sharing lists and dictionaries. So what I end up doing for sharing data, I usually just copy the data to multiple interpreters, and that there's two downsides to that. One is that I have to spend time copying things over and then copying things back when I'm done. And the other downside is that uses a lot of memory. So the third approach also used in this project is to do multi-threading using C++. So in this approach, the execution mode, normally it's in Python, right? And then it jumps into a C++ execution mode. And in that mode, I can run multiple threads on multiple cores. And that's the mode I use to solve the least square problem, the ALS problem. And the final approach used in this project is clustering. Clustering means multiple computers. A cluster of computers means multiple computers. Now the computers come from Amazon, the Amazon EC2 service. This is basically renting computers from Amazon. And the computers need to have a shared file system. So this is Amazon, right? So I'm renting computers from Amazon. So the file system that I use to share information is the Amazon EFS, the Amazon Elastic File System. And so I have clustering here because I added clustering to this project because I think it's an important methodology in solving problems. But keep in mind that clustering is not, a lot of situations because you're doing this on Amazon, you can also choose to go to more powerful instances. So you could have more computers or you could have more powerful computers. And Amazon has some really powerful computers that you can rent. So EC2 instance types, and point out the most powerful instances in conventional computing it's in the memory optimized section, high memory. These computers have 12 terabytes of memory and hundreds of cores. So you might not need a cluster. You just get a computer that has hundreds of cores and terabytes of memory. Amazon also has GPU instances and FPGA instances. And the point is that if you buy these machines, if you buy this thing, it will be a huge amount of money. I think these cards, these Tesla cards, are like maybe $10,000 each or something. The point is that if you actually buy a machine, it's a lot of money, but you can rent one from Amazon for a much more affordable cost. So that's the point that I'm using clustering, yes, but you might not need it because Amazon has really powerful instances. Okay, now I want to talk about the add.py program that's under basics multiprocessing. I think it's important to study this program. It illustrates how I use multiprocessing to process data. Even if you have experience with C++ or Java multithreading, I think you should still study the program because multiprocessing in Python is quite a bit different from multithreading in other languages. So this program uses multiprocessing to add two lists. And after adding the two lists, the program will check it, just and check it by doing the operation the standard way, which is multiply by 5 and then add it together element by element. So if you run the program, it will just tell you that the check succeeded. So computed the results correctly because I match the results. So I'll go over the program from a very high level first, and then I'll kind of delve into the details. Because this program shows the basic multiprocessing pattern. So first, start processes. This function will spawn additional Python interpreters. This part generates the lists that will be added together later on. this function splits up the list x1, splits it up into 4 pieces. I have 4 cores. I have a quad-core CPU, so it splits it up into 4 pieces and sends it to the 4 interpreters. And do the same thing with x2. Run function tells each interpreter to run a function. So the operation I'm trying to do is x1 times 5 plus x2. So the first function to run is the multiply function, and then run the add function. So at this point, this result is spread across the 4 interpreters in 4 separate lists. So the final step is to combine these 4 lists into a single list. And at the end, clear the data, because tell the interpreters to clear the data that they allocated to do these operations, so to save memory. And the final step is to terminate the interpreters that got spawned earlier on, that got spawned via start processes. So that's an overview of what the program does, and I'll kind of go into a bit of the details. So the program is structured so that the multiprocessing code is in this file. It's in a separate file, and that's a naming convention that I follow for the remainder of this project, is that the primary file, the single threaded file, is in it's something.py, and then the multiprocessing support file is in _proc.py. The multiprocessing file is there to simplify the main file. So the main file looks kind of simple. It, split things up, run a function to do computation, combine the results together. The background file is also there to restrict variable visibility. So these variables x1, x2, they represent the full list. This background file cannot see that, even if by mistake. This is important, and I'll kind of go over. I'll return to this point a little bit later. So the individual interpreters, they are actually getting the data from this variable. I'll talk a little bit more about this a little bit later. But the point is that they're not getting the data from x1, x2 directly. And this file is supposed to be a bunch of reusable building blocks. So all these functions, start processes, end processes, send same data. These functions are meant to be reusable all the way up to the bottom. So for me, this is kind of like a framework. So multiply and add are application specific. It's just that in this application, I need to multiply and add. But the other functions are meant to be reused down the road. So the first thing I do is start processes, and this spawns additional Python processes, Python interpreters. And so this is the first difference between, say, Python and some other, and C++ multithreading. So I'm actually spawning one less than the CPU count because I already have a process. So the very first interpreter, let's call that interpreter 0. The interpreter 0 is spawning interpreters 1, 2, and 3 for a total of 4 interpreters. Normally in C++ multithreading or other multithreading, you want to spawn the number of threads equal to the number of cores, and then the parent thread that did the spawning, they'll just enter blocking mode and they'll just wait for the workers to finish. But Python, it's a little different because Python interpreters are a lot more expensive than C++ or Java threads. And also they can't share data directly. They can only share binary data. They can't share like lists and dictionaries. So I have to copy, I have to duplicate data. So Python processes are more expensive and they use up more memory just because they can't share memory in between. So it's important to spawn as few processes as possible. So it's -1. And the main thread, the main interpreter 0, after they spawn it, they just quit. Now the interpreters 1, 2, and 3, the worker interpreters, they're gonna be in the message loop. So they just listen to messages and handle requests, and they just stay in the message loop. And then when they exit the message loop, those interpreters will exit. Eventually, they'll get a shutdown message, and they'll just exit the message loop. And then the interpreters 1, 2, and 3, they'll just exit that way. But interpreter 0 will continue to run. That's the primary interpreter, the original interpreter. And I want to demonstrate that Python is actually spawning multiple interpreters. I can demonstrate that by adding some print statements. So first I'll add a print statement here. And I'll just copy this. So this, when I hit this line, that means I'm gonna spawn additional interpreters. And I'll have another print statement here. So I hit this line, that means I am importing the math library and the random, I'm importing the FAPS function, the random function. So as you can see, let's call this interpreter 0. Interpreter 0 starts and it imports a function, and it starts off 3 interpreters. And notice that each interpreter that got started will also come here. So let me repeat this. When I start an interpreter here, I don't just spawn a thread. I spawn a whole new interpreter. That interpreter goes back all the way to here, goes back to the very beginning, and then it will import all these libraries all over again. So, those Amazon machines that have like 400 cores, and if I'm spawning 400 interpreters, well, it's gonna import NumPy or whatever 400 times. That's the big difference. That's why it's so much more expensive to spawn interpreters as opposed to spawning threads in C++. And actually, this is a Windows thing. Windows will do this. Will kind of like, it starts out all the way from the very beginning and import everything and basically rerun this whole thing. Linux, I don't think you see this message in Linux. Let me remove that now. I don't think you see this message in Linux because Linux has a split. Linux has a fork system call, so Linux can clone processes without fully restarting the processes. But the end result is the same whether you're in Windows or if you're in Linux. You're gonna have 4 interpreters, and they're like clones of each other. Each interpreter will have all these variables that you see here. They all have processes and pipes, and not all of that is gonna make sense. So that goes back to my point of isolating variables to prevent the worker interpreters from seeing too much. Okay, all interpreters will have all these variables, but those variables are different because those interpreters are doing different things. The end result is that not all these variables can be trusted. Okay, so interpreter 0, the very first interpreter, that interpreter can trust all these variables. They're all real variables. But interpreters 1, 2, and 3, these variables are going to be obsolete very soon. So the convention I use in the program is that interpreter 0 can trust all the variables here. Interpreters 1, 2, and 3, they can only trust the connection variable. This is the connection to interpreter 0. And they can also trust this variable. So every variable has a different set of process data. Okay. So after starting the interpreters, I chop up the list and send it to the 4 interpreters. So I'll go here. So I figure out what indexes do I use to split the lists. Okay, so pipes represent the connections to the interpreter. So this part is interpreter 0, the original interpreter. Interpreter 0 will send sections of the data list to the worker interpreters. And then the final, so I have 4 cores, right? So the first quarter, second quarter, and the third quarter are going to be sent to the worker interpreters. But the final fourth is saved locally it's copied locally to process data. And this is not copying, right? This is just copying a reference. I don't think Python actually duplicates the list. It duplicates a view of the list, so to speak. Okay. So interpreter 0 gets the final fourth of the data list. Interpreters 1, 2, and 3 are going to get a set data message. And then when they handle this message, they're going to put the data list in the process memory. So basically, interpreters 1, 2, and 3, they're stuck in the message loop. They get the set data message, and then they'll put this list into the process data. So that's sending data to the interpreters. This is run function tells the interpreters to run a particular function, in this case _multiply. So I'll go there. So again, this is interpreter 0 executing run function. Interpreter 0 will send messages again. So pipe for every connection send the message. And then interpreter 0 will just run a function using, this is Python's reflection mechanism. It allows me to run a function, an arbitrary function name, by grabbing it from the global namespace. So that's interpreter 0. They send messages and they run functions. So the other interpreters, okay, the message name is called run function. So interpreters 1, 2, and 3, they're stuck in the message loop. They're gonna get the run function. They'll get the run function operation, and then they're gonna kind of decode it, get the function name, and they will call global's op name. They'll use the Python reflection mechanism to run functions. So that's run functions. Concatenate into lists, concatenate variables into list. So you know the pattern kind of already. This is the third time going over it. Interpreter 0 will send messages, okay, get var, and then interpreters 1, 2, and 3, they're gonna handle the get var message and send back the reply. Interpreter 0 will get the lists, the list fragments from interpreters 1, 2, and 3 via the pipe. And the final list fragment is provided by interpreter 0. So that's me going over roughly how this add data.py works. So now I'll talk about the project to use C++ to solve the least square problem. So first of all, I would rather avoid C++ if I could. But what happened was that the SciPy algorithm for solving least squares is too slow. So in the basics directory, there's an LSMR file to demonstrate how to use SciPy's LSMR and also LSQR to solve the AX equals B equation. But so the original hope is to just use those to solve this, but it turned out that they're actually quite slow because they're single-threaded. So in the basics/multiprocessing directory, there's a LSMR and I was MRProc. And what I found out on my computer, it took 165 seconds to solve AX equals B when the A matrix is 27 million rows. So this is to simulate the actual problem encountered in using ALS algorithm on the full data set. So, and the reason it took so long, the main reason is because it's single threaded, and there's really no hope of making it faster by running it on computers with more cores because it's single threaded. And that led me to develop the C++ program to solve the least squares. So the documentation is down here. C++ least squares. I'll go over the project. There's a least square project located at cpp/ls. This project is pure C++. Then there's a wrapper project, cpp lslib. This project is also C++, but the goal of this project is different from the previous one. This one builds a DLL file or SO file. So on Windows, the share library is in a DLL file, and on Linux, the library file is in an SO file. And then there's a third project at cpp/python. This project contains a wrapper written in Python, and also it shows how to use the wrapper. So that's a quick overview. I'll go over the projects in more detail. Oh, the algorithm is from the book Numerical Optimizations, 2nd edition by Nosodal and Wright. It's algorithm 5.2, conjugate gradient. This project, the LS project, when I run it, it looks like this. So the project does two things. It checks for the correctness of the algorithms, and it does some benchmarking. So there's C++ routines for adding vectors, vector dot product, matrix multiply, that's matrix times a vector, matrix transpose multiply, that's a matrix transpose, times a vector, least squares, conjugate gradient, CG stands for conjugate gradient least squares, a second version, and there's an ALS function. So one thing of this project is to check for the correctness of those algorithms, and the other objective of the project is to run benchmarks to see how fast these functions run. And I want to mention this. Oh yeah, so over here the project tests the ALS. So previously in basics, there's a project that tests the ALS, and when running this project, the error is very low. It's like almost zero. Well, that's because in this project, the data, when I generated the data, it doesn't have any noise in it. But in this project, in the C++ version of the project, when I generated the data, I added a noise to it. See if I can locate that. Okay, so let me put this here. So the project has 3 files. This is the least square project. It's 2 here, and there's a header file. So for a total of 3 files, there's the matrix and the matrix header. Those implement the operations and the algorithms. So if I can collapse this. So the matrix, I can do this. So there are classes like array, that's just for memory. So column vector, matrix, sparse matrix, adding, dot product, randomization, that's for testing, vector times a constant, And there's also global functions like ALS and conjugate gradient. So all the operations and algorithms are in the matrix .h and the matrix.cpp. The main function is for benchmarking and testing for the correctness. So the benchmark functions, and there's also testing functions. There's a flag in the main. That's right. I'll just here. So in the main function, there's a flag use small data sets. So what happens is when I set small data sets to true, the benchmarking function will use rather small vectors and matrices, so things run quickly. I can set that to false to simulate the full data set with 27 million, with vectors that are 27 million long and matrices that are 27 million tall by 280,000 times 10. So I can set, so basically to benchmark in a realistic situation, you need to go into the code and change this to, to false and then run the benchmark. Okay, so actually I was originally saying the ALS from the basics, that version, that Python file produces very low error because when I generate the random data for testing, I did not inject any noise into data. And I'll see if I can find a noise on here. So it's test ALS and generating data. So I'm generating data here, and then when I'm generating data, I'm putting in normally distributed noise. So that's why this ALS has a much higher error. The error is non-zero, so that's why. Okay, and then I want to go over the benchmark section. So one thing to note is that conjugate gradient is an iterative algorithm, and these problems that I'm benchmarking using randomly generated matrices. I'm not benchmarking using the actual data set. I'm benchmarking using randomly generated matrices, and then conjugate gradient requires an initial condition, which I also generate randomly. So random data, random initial conditions, and so the number of iterations, it's gonna vary a little bit. So I do this 2 times using algorithm 1 and it's 59 iterations. And I do it 2 times using algorithm 2 and 67 algorithms. That doesn't mean, algorithm 2 is necessarily more iterations. It's just that the random data and the random initial condition maybe have more iterations. So the key metric is actually time per iteration over here. That's the metric to pay attention to, and this shows that algorithm 2 is slightly faster because per iteration time is slightly shorter. I'll talk a little bit more about this later on. Basically, ultimately, I ended up using algorithm 1. So algorithm 2 is only faster if there are lots of iterations. And in the actual ALS dataset, there were far fewer iterations. And the benchmarking, okay, so this benchmarking, so this benchmarking is rather small matrices. It's not 27 million rows. It's only 1,000 by 100. So this is done using the flag the small dataset flag. Let me show the main function here. Because of this flag set to true, I'm using the smaller size benchmark. So I have done the benchmark using the full size matrix on AWS and also on my own computer. The benchmarks are here. So my computer, it's 6-year-old computer, Core, the 3000 generation, a quad-core computer. And this is AWS. This is their spec. And I can run the benchmark under different threads. So that's a command line parameter. So you pass in a number. So if you pass in 5, it's going to run with 5 threads. It sets a thread count, which is a global variable. So pass in a 5, thread counts get set to 5. And that's a global variable, and they're using the extern. Show the extern. Yeah, oh, it's over here. So that's how the thread count got in. Oh, back to benchmarks. Okay, I was talking about the benchmarks, and I want to say that more threads is not necessarily faster. It kind of gets faster and faster up to a certain point, and then the improvements start to kind of level off. And sometimes, like over here, more threads is actually slower. This is basically, this is in general true. It's because that the memory cannot keep supplying the CPU with enough data. So the CPU is waiting for the memory to supply more data. And I shaded in the point of diminishing return. That's basically when I'm doubling the thread count, but it's not really, the speed is not doubling. And that's important because on AWS, when you get an instance with twice the number of cores, Amazon will charge you twice as much. But in general, you're not getting things done twice as fast. So in general, you don't automatically go to the largest machine possible. So right now, as of right now, in January 2019, this is the highest number of cores possible for the compute optimized instances. So, but I use that for benchmarking. Doesn't mean that you should go to the largest instance possible. Okay. Yeah, and over here, like I said before, I only recorded the time per iteration. But if you run the program, it's going to tell you the total running time and the time per iteration. So go over documentation a little bit more. Yeah, like I said, the source of documentation is this textbook, a very popular book on optimization. And I went over how you control the number of threads already. You pass in a number when you call the program. Well, it doesn't mean it's main. Okay. The name of the program is ls. Actually, it depends on your project settings. The name of the program. So there's some. We will need to build the program on Linux because that's how the benchmarking is done. It's done on Amazon Web Services, AWS. It's done using Linux EC2 instances. So that's a command to build the program on Linux. The output of the program is main. So that's why it's called main. I already talked about this. and some documentation about what all these functions do. And yeah, I'll talk about this. This ALS is using a sparse matrix, so there's several ways to store sparse matrices, and I have an example on how I'm storing it, basically. So that's documentation on how to store sparse matrix, how to access my sparse matrix. And this is documentation about transpose multiply. Transpose multiply means that AT times a vector. So transpose of A times a vector. This is the project bottleneck. Back to the benchmark section. Transpose multiply is the thing that doesn't scale well. So if you look at multiply matrix times a vector, and that scales pretty well, right? You know, it stops improving at twice the rate, but it's getting better and better. It's just not doubling. The speed's not doubling, but it is getting faster. But transpose multiply, it stops and then it actually becomes slower. So right there. So the optimal speed is 18 threads on a 72 core machine. It's probably more than one CPU. I'm not sure, but so this is a bottleneck because I'm trying to find ways such that this will continue to get faster and faster, so then I can run more threads and lower the speed. As it is, you know, more threads actually slow down this operation because the memory can't keep up with the CPU. So that's why I meant that it's a project bottleneck. So transpose multiply has two. I deal with it in two different ways. One I call direct multiplication. So ATV is computed without actually computing the transpose. So I'm multiplying the matrix A and the vector V in such a way that the result is equivalent to ATV without actually computing transpose. So this talks about what I'm doing there, how I'm doing it. And there's an alternative to transpose multiply that is actually computing a transpose and then multiplying by V. So going back to the benchmarks a little bit, if I compute the transpose, then I'm using standard matrix multiply, and this is scaling better, and standard multiply is also faster than transpose multiply. However, it takes time to compute the transpose. So on my machine, it took 6 seconds to compute the transpose. And this is 10 multiplications. So if I do transpose multiply, option 1, I use this. I do 10 multiplications. It takes 8.4 seconds on my computer. Option 2, I compute the transpose. And then I use standard multiply. So 6 seconds and 5 seconds, totaling 11 seconds. That takes even longer than this 8 seconds. So clearly, which way of doing the multiplication, it depends on how many iterations there are in the conjugate gradient algorithm. That's why over here, this is running the program benchmarks on a small matrix, just 1,000 by 100. If there are sufficient number of iterations, algorithm 2 is computing the transpose and then doing the multiply. This is faster, but only because if there's a sufficient number of iterations, So according to this benchmark, if it's only 10 multiplications, I think that's like 5 iterations, because each iteration you do 2 of those, or is it 1 of those? Anyways, if you don't have enough iterations, it's faster to use the transpose multiply, the matrix transpose times vector, to use this routine. And just skipping ahead a little bit, in the actual data set, when I actually use this routine on ALS, there aren't that many iterations, and so algorithm 1 is the one that's default. Algorithm 1 uses this transpose multiply. So in the code, there's 2 algorithms. There's least squares and least squares, algorithm 1 and 2. I'll talk a little bit more. There's some notes on how the ALS matrix is constructed. And there's some notes on termination. So the algorithm is from the book, algorithm 5.2, but the book doesn't say how to terminate. Like, when do I stop doing this conjugate gradient thing? And the termination is based on a percentage decrease in residual term. I actually did a bunch of testing. Like I said, these matrices are these tests and the benchmarks. They're using randomly generated matrices. So I did a whole bunch of testing, and this technique seems to work. Percentage decrease in residual term. I noticed that in my testing that conjugate gradient gets stuck sometimes. So the percentage decrease criteria has to be met on 2 consecutive iterations, because the algorithm tends to get stuck. But it seems that my termination condition seems to be okay. So next up is the library project. Okay, so the LS project, what I call is SCPP/LS, that's a pure C++ project that develop routines in the matrix CPP file and then test those routines in the main.cpp file. But that's pure C++. So in the library project, cpp.lib, the focus is to build binary libraries that can be called from other languages, including Python. So this one also has a CPP and then CPP and the header file. Oh, this is from Windows, so a little bit more about that. Basically, I just used the project Wisher and I created a Windows library project, and Microsoft puts this and also this in there. So the library project, the output of the project is the DLL file for Windows and SO file for Linux, and those are the files. So the matrix files, matrix header, matrix CPP files are utilized by both Windows and Linux. But Windows and Linux, they do share libraries differently. So to build on Windows, you need this file. To build on Linux, you need this file. And the difference is how they define the entry point to the library. To build on Windows, you create, a project, new project, and then there's a Wisher, and then you create a Windows library project. And then that's where all this other stuff comes in. This stuff, I think this stuff. I just left in there because those are there from the project Wisher. But for Linux, you build the project using this command. You need those 3 files, these 3 files, this, and this. So that's a command to build on Linux. So some changes. So it's a little bit different. So this matrix. Okay. So the least square, the LS project has a matrix file. Collapse it. Okay, so the least square has a matrix file, and the what I call the least square library, the Windows DLL. Okay, this project also has a matrix file. These 2 matrix files, okay, oh, it's over here. This one and this one, they're slightly different. So one difference is that the earlier one, the first matrix file, it's a pure C++ project. So in that case, all the memory, the C++ needs to clean up all of the memory by itself. And in this version, in the library version, in this version, the data is externally allocated in by Python. So there's a flag basically so that the C++ code will not deallocate certain arrays, because those arrays are allocated by Python, and Python's garbage collection will clean up those arrays. There's also this use sorted row feature. Okay, so in the original project, in the CPPLS, the first project, pure C++ project, I did the benchmarks, and then I realized that this is a bottleneck, and so I had some ideas on how to improve it. And this row reordering idea, and I felt it was kind of interesting. It did not work out. But I left the code in there in the original CP in the original matrix.cpp. Even though the idea did not work out, I thought the idea was kind of interesting, so I left the code in there. But in the library version, the cpp/lib, in that version of the code, I took out the related code and took out the flag, because the idea doesn't work. So and that's the project. And like I said, there's a command to run it, to build the SO file. On Windows, you run the project to build the DLL file. And this is just me saying that I need to manually copy the DLL file to the Python directory. So this project builds a DLL file, and I need to manually copy that to this project, because the Python code is just going to look into the default directory, the current directory. So this is the cpp/python. So like I said, the DLL file is not from this directory. It's actually built somewhere else, and I manually copy it to this directory. That's what I meant. cpp.py is the Python wrapper for this DLL. And the ls_test shows how to use this wrapper. So I'll just run that. So this Python, this is like a test file. It, there's a function to check, has the DLL been loaded. cppls, like I said, cppls is the wrapper for the library file. So the test file shows how to use the least squares to solve least square problems, and the test file also shows how to use the ALS. And like I said, there's some error in there because the data has noise in it. So that's the overview of the multi-threading using C++ project. So now I would like to go over the basic cluster computing example that's located at basic/distributed work. So I'll go over this. So this is the documentation under distributed work, and this diagram shows the basic idea. There's a cluster server that manages the workflow, and then each worker node runs a worker server program. This worker server program then spawns 4 different interpreters, the worker process.py interpreters, because this picture is assuming that the worker node is a quad core computer. So that's why the 4 Python interpreters. So the user runs the add.py. Add.py adds two lists of numbers together, but it's adding it using this cluster computing setup. So add.py submits a request to the cluster server. The cluster server then farms out the work to worker server. So that's the basic principle, that there's a single cluster server, there's multiple worker server programs, and there's a single add.py. And yeah, this black box here, this is one computer. So the worker server is communicating to the worker process programs via pipes. This part of the example is identical to the multiprocessing example. What's new here is the TCP part. So the user's add.py is making a request to the cluster server via a TCP connection, and the cluster server is farming out the work via another TCP connection. I like to point out, it's not in this picture, but the TCP connections are only for short messages. In particular, TCP is bad for broadcasting. TCP is a point-to-point, one socket per conversation kind of protocol. And in distributed computing, what happens is this worker server will make a modification to disk, right? And all the other worker servers and also the cluster server and add.py would have to know about that. So that's like a broadcasting kind of operation where one node makes a change and all these other nodes have to know about it. And that's why for large amount of data, the data is passed via the file system. So when I'm running on my machine, like local demo, I'm using all the worker servers. They have the access to the same hard drive. So that's a file system. But in a more realistic situation on Amazon, the file system underlying the cluster is the Amazon Elastic file system. Okay, so I'll run the program now and show how it works. So to run the basic demo, the cluster computing demo, run the cluster server first, and then run the worker server, and then run the add.py. So, the demo said basics / distributed work. So first the cluster server, and when you run this, there will be a JSON file created under the bin directory. Let me bring that up. Yeah, so this file is at distributed work bin directory. It's in the bin directory, and it's called clusterinfo.json. So I just ran the cluster server. The address is 192.168.166. So that's the information. So when a worker server joins the cluster, it looks for this JSON file and it gets the address here, and then it gets a port number. That's how it knows where the cluster server is located at. So I'll do that next. Okay. So first the cluster server program, then the worker server program. So Python. That's the wrong one. That's the wrong one. The worker server. Okay. So worker server at this using different port. Now I'm doing all of this. I'm doing everything on the same computer. So the only difference is really the port number. The IP address is always going to be the same. But of course, in the real cluster, these should be different computers. So when I ran this, the cluster server, this is the cluster server program running. It says a new worker node has joined with 4 CPUs because it's a quad-core computer. And show the program. Okay, so this file got updated now. So this JSON file, the very first entry, that's the cluster server entry. There's only one cluster server, and all these other entries are for worker nodes. Okay, so the third thing you have a cluster server running, you have a worker server running, and the third thing is to run the add.py file, which adds a number, but it tells the cluster to do it. So creating input.bin, like I said, the files are, the information is being passed around mainly through the file system. Only short messages are being passed around through TCP. So the files are in the bin directory, and that's set in the cluster.py file. So add.py is generating 2 random lists, and then these lists are saved to the input.bin file, which is what you saw here, creating input.bin. And well, now it's adding stuff. And you can see the cluster server farming out the work well, it's farming out to always to the same node always, because that's the only node that I have. So cluster status. This cluster.py is an interface to the cluster. So it's reading this JSON file. That's how it knows who to talk to. So you can import in the Python interactive window. You can import a cluster, and then you can do print status, and it's working on the add right now. As it works on the add, there's a timer. Here, there's a countdown, an estimation on how long the ad will take. Well, the ad's taking a long time because it slowed down on purpose. So right there. So proc run function add. So the add function. Yeah, so there's a time.sleep function that to make it add really slowly, so I can actually see stuff happening. And still a minute to go. I can add another process, add another worker server. So normally this would be a different computer. So this is a bin directory. So in the documentation, I mentioned how to simulate having multiple computers. So normally you just type this in, and the default port is 10,000, but I can give it a port number, and that's my way of simulating having a different computer. So it's still a minute, but I can speed that up. So if you look at JSON file, the JSON file now has a new entry for the new node at 10,002. And if you look at timer, it just went down a lot because of this new node helping out with the addition. So this system estimates how long it takes, and then as I add new node, the estimation will be updated almost instantaneously. And just waiting for it to finish. Okay, when it's done, it's gonna check for this. So the worker nodes are okay. So the addition of the 2 lists, they're broken down into many segments, and so so toward the end, so in the beginning, it's just sending out to the 10,001 port. Later on, it's kind of alternating between 10,002 and 10,001 here, because I added a new node to join the cluster. And all these are like, so when the computer adds like index 7,000 7,817 to 7,868, when it adds that subset of the list, it's going to save that to the hard drive as a temporary file. And now that the process has completed, the temporary files are erased, but you can see it. You can see the temporary files while this is running. At the very end, there's in the bin folder, there's the output.bin. So the add.py generated the input.bin, which contains the two lists that are to be added up. And at the very end, the outputs, so each of these is like a single output file. So and at the very end, I merge all the output files together into a single output.bin, and that contains the final list, the sum of the two lists in input.bin. So also notice how the program is printing out how much work is being done by each node. So in this case, yeah, the IP address is the same, but it's fake. But in a real situation, the IP addresses will be different. The port number will be the same, but it's printing out the total number of units done by each node, and also the total time spent. So actually I restarted the example because I made a mistake. And in this time I restarted the filming because I made a mistake. So in this time I had node 10,002 join almost immediately. So in this run through, that's why the 10,002 node has almost the same amount of work as the 10,001 node. And they have the same, this is the amount of time per unit. That's total units divided by total time. So that's the amount of units of work per second. So it's making 40 additions, roughly 40 additions per second, which is really slow, but that's slowed down on purpose, of course. As I like to say, this part is really important. It's important to know how much each node is doing, because Amazon right now has a lot of different instance types. Amazon has the A1, which is an ARM instance, and Amazon has a lot of Intel instances, and Amazon added AMD instances. So there are 3 kinds of instances on Amazon, and among the Intel instances, you have compute optimized and memory optimized. Usually compute optimized is the best deal because they have the least memory. But anyways, the only way to know what instance to use is to benchmark things and to know, how much work an instance is doing versus how much an instance is costing, how much Amazon is charging you for the instance. So next I'll go over the documentation file. So basics distributed work, and this tells you what commands to run. And like I said, there's a way to fake having multiple computers without actually having multiple computers. To just give it a new port number, and then this worker server will be recognized as a new computer. Here's a diagram. This talks about the JSON file that, the first entry is the cluster server and the other ones are the workers nodes. This is a list of the messages. The system works by having the computers passing messages around. So these are messages, call trees. Oh, there's a sequence of events here. When you run this add.py, this tells you what happens. I'll roughly go over what happens via the code. So add.py, well, it generates a problem, a random list x1, random list x2, save the list as input.bin. So let me see. Yeah, so that's creating input.bin. That's the binary file that has x1 and x2. And then it submits a message to the cluster.send command. Now cluster comes from import cluster. So when the cluster is imported, it looks for that share file that I mentioned, the cluster.json file, the file that looks like this. So the first entry is the cluster server. So that's how add.py knows where the cluster is located by reading this file. Okay. So it knows where the cluster is. And there's an error message, if that file is not found, if that JSON file is not found, it will say cannot connect to cluster, exit. Okay. And if it finds a cluster, it's going to send an add operation. And then you can go through the documentation for details, but this add message to the cluster eventually becomes an add setup message followed by an add message to the worker server. So very early on, it will tell it gets an add message. It didn't really print out that, but the worker server will print it out. See, the very first message is an add setup, so like get ready to add things, and then after that's done, there will be a add message and more add messages, all these add messages until it's done. Okay, so to recap, add.py sends an add message to the cluster, and eventually somehow this becomes an add setup message. And what add setup message is get ready for add, and I'm getting ready for add by loading that input.bin file. Remember all the workers, all the cluster server and the worker server and the add.py, they share the same hard drive. They share the same EFS, AWS EFS, the same file system, so they can see the same files. So to prepare for that, I load the x1 and x2 from the input.bin. And here comes the actual add, and the add is broken down. Like this command is to add 723 through 1006. Yeah, the total is 10,000 numbers to add. So add those numbers, and that's where I get the start. I get the length. Okay. Yeah. So here you see 723 through that. Okay. So what actually gets passed out is 723, the start, and the length of 284. Okay. So I get this. I get the start. I get the length. I add that, and this is done using the multiprocessing technique mentioned in the previous program. Oh no, in this one. In this one. So it's done by the proc helper file. The proc is this one, worker process. Run the add function. Concatenate the sums. Okay, so this 284 is broken down further into 4 pieces to be added by the 4 interpreters on my quad-core machine. And then after I finish adding it, I write it to disk, call output.bin. But it's not really this. It's actually output.bin, but it has a number attached to it if you write output to disk. So there's an output file name. Yeah, file name is output.bin, but it has a sequence number. So the final file at the very end is called output.bin, but all the temporary files will be like output.bin dot some kind of sequence number. So that's what the worker server does. It adds numbers, adds a subset of the list, writes it out as output.bin dot sequence number. The sequence number is the start. So the worker server handling this will create an output.bin file, output.bin dot 723, and this one will be output.bin dot 1007. So lots of output.bin files dot something, and then at the very end I'll merge them all into a single output.bin file. Keep going over documentation. Mention else here. Okay. So when I made this cluster computing basic examples or some software requirements, I want to have a completion time estimate. So as the add.py file is running, there's a timer that sort of counts down to 0. That's the completion time estimate. It distribute processing to new worker nodes as they join. So when I start up a new node, this timer just got cut down by half because of the new node that is joining and sharing the work. Health check, so to use AWS Spot instances. So AWS Spot instances has a health check system. So here's an advertisement for AWS Spot instances. Compute at up to 90% off. It's not 90% off. It's like 60 to 70% off usually, which is still a lot of savings. So you want to use AWS Spot instances whenever possible. But to fully comply with that, I have to check a URL to do the health check. So I mentioned it a little bit more down here in the AWS modification section. Messages, yeah, they pass messages around. It's call tree worker. Okay, worker state, I want to talk a little bit about that. Worker state, that's the worker server program, and it starts off in idle state, and there's a setup, working, and cleanup. Cleanup is just deleting all the data in the memory. So when it's set up, it puts stuff in this data, underscore data, and cleanup is deleting this stuff, basically. So that's where the messages come in. The messages are kind of automatically generated. So the add.py submits an add message, and the add becomes add setup, add, and also add cleanup. And those messages corresponds to the stages, the working states of the worker server program. So when the worker server is in this state, it's doing the add setup message, and this is doing the add message. Cleanup's always the same, so I didn't explicitly have code doing that. Oh, next part. Yeah, I think the most complex part of the project is estimating the completion time. That's the timer you have seen over here that kind of counts down. So I have a section in the documentation talking about it. And AWS modification. Okay, so they were saying this is, well, not 90% off, but it's like 60 or 70% off. So what's the catch? Well, the catch is that Amazon can take those instances away from you at any moment. And when Amazon takes them away, they're going to post a special message right here. Okay. So normally request is the Python request package that queries in URL. So normally querying this URL will get 404. So that's good. Right, okay, because that means there's no instance action. And if the error code is not 404, then there's a cancellation notice from Amazon that your instance is being canceled. Okay, so to understand this, every time, so right before this is the cluster server, okay? This is the cluster server. So right before the cluster server ask the worker to do this work, the cluster server is doing a health check in the form of an echo message. So that's why before every single add message, the add message is to do work. Before that, there's an echo message. That's the health check. So the standard health check is an echo message. Echo message is right here. Operation is echo, and the value is a random number, and the response is a reply, and the response value needs to match the request value exactly. So that's how it's checked. server. Okay. So when I'm running locally, AWS instance is off, and health check is the echo. Okay, and I reply using, if the value is 404, whatever I reply saying is 404. So that's normal operation with AWS instance equals false. Now, when running in AWS mode, I need to set that to true, and then I check the CRL, and if there's no cancellation message, I'm gonna do the same thing as I did before. I answer the echo with the same number, right? But if there's a cancellation message, I add value to 1 to the echo. So the echo will be incorrect. Okay, so if code is not 404, if status code is not 404, then there's a cancellation notice. And I'm going to increment the value being this value in the echo command. When I increment the value in the echo command will fail, and the cluster server, upon seeing a bad echo command, will remove the node, will tell the node to shut down, and then remove the node from the list of working nodes. So then the cluster server won't ask that node to do any more work. So that's how I comply with the spot instance requirement. That's a spot instance requirement, that your code needs to be able to handle Amazon's cancellation messages. So that's the theory. Now, actually, there's another way around that I want to talk about that. So if you actually launch an instance and you get to here choosing the purchasing option request spot instance, and there's a maximum price. So what happens is when the price exceeds the maximum price, the Amazon will cancel your instance, and they'll have this that's where this mechanism kicks in. But what I usually do is I don't specify a maximum price. I'll just pay whatever Amazon wants. And so far, I've never gotten a cancellation message. So that's actually what I'll do in this demo later on in later slides when I run this stuff on Amazon. I'll actually just not set the maximum price. Then, as far as I can tell, I never get this cancellation message. And then I never actually have to do this instance equals true. I'll just use the echo command for health check. So that's me explaining how do you use spot instances. Just don't set the maximum price and treat it like a normal instance. Windows occasional crash, you can read about it, but it doesn't matter. Yeah, this might fail on Windows. So Windows has two things. One thing is sometimes the program will freeze if the window has the keyboard focus. So you just have to hit a key and to get away to relinquish your keyboard focus. Okay, but this is talking about there's some kind of networking failure. I have a run echo test to stress test the server. But this crash never happens on Linux. I want to say that. So anything that happens on Windows, but it's okay on Linux, that's fine with me, because Windows is for development only. So here's the EC2 spot instance pricing. There's a Windows column. Okay, there's a Linux column, and there's a Windows column. And currently Windows is like 5 times more expensive here. Like 5 times more expensive, something like that, right? Sometimes it's 4 times more expensive. Like this is 4 times of that. Sometimes it's like 5 times, more than 5 times. Yeah, so Windows is way more expensive than Linux, and Windows is only for development purposes. You develop on Windows, but you deploy on Linux. So this thing doesn't matter, as long because it's okay on Linux. There's a networking error on Windows, but not on Linux. And that's my summary of the basics/distributed work demonstration of how to do cluster computing in Python.